Thank you very much, Marcella, for this introduction, and good evening to everybody. It's a big pleasure for me, but also an honor to be here and to speak a little bit about what I have produced in the last 25 years as a civil engineer, together with my colleague Kerez, architect, and we, with our civil engineering office, work together with a lot of different architects, but I think the cooperation with Christian was really the strongest and the deepest one, perhaps also the most radical. And this is the reason why I will focus this evening on projects we developed together. I will show, after a not so short introduction, I will show 3 projects we developed and built several years ago, and 3 other projects much more recent, and the last one not yet built, but still in the phase of planning. It's very important for me to give a small introduction because I think to really understand what's the background of this cooperation, it's perhaps not so bad to tell you a little bit about my own philosophy on structural design, on what structural design could be, and what we always tried also to do when we were developing projects. On our chair, the term structural design denotes the programmatic idea of reconciliation between the disciplines of engineering and architecture through the reciprocal integration of load-bearing structure and architectural design concept. A nice quote, but I think to explain a little bit what we are understanding under this quote is on the one hand that we see these 3 different elements that are very important for us: the material, then the force flow, and the architectural concept. And we have the feeling that these 3 elements have to come together really from the very beginning. That must not be the case for all the projects, but I think for projects in the sense that I will try to show you, we feel that this is very, very important to bring these elements together really from the very beginning. Material is, yes, what is material? Under material we are understanding on the one hand the material as a building material, but on the other hand also the level, let's say the level of construction, perhaps in the sense of Kenneth Frampton construction, bringing elements together, and this seems to be a very, very important issue in the whole process. On the other hand, we have the force flow, perhaps more in the sense of Rudolf Rettenbacher. This could be the way how to articulate forces in space, how to articulate forces in the building elements. And one problem that civil engineers are always confronted is that with classical methods, they are on the one hand only able to analyze an already given structure. Then they have models to modelize the force flow, and they have other models to analyze how elements are coming together. And for us, it was very important to develop a procedure that is able to overcome these problems, to bring already on the civil engineering level these elements together, and on the other hand, also to visualize what we are doing. And only then it's possible to come in a good discussion from the very beginning with architects, trying to speak more or less a similar language in the sense of discussing, in the sense of understanding what space is, in the sense of understanding what the envelope of a space is and how this envelope can be articulated and how these different elements can be brought together. And in this sense, structural design is really in between these three different elements, and I will try a little bit to explain what we are understanding under this. If you are looking at this very well-known bridge of Robert Meyer, Sarginatobel Bridge, built 100 years ago, for sure Robert Meyer was not only looking at the classical ways of developing bridges. Yes, there is the quote that he was pre-designing bridges on old, already used letter couverts, and I think this can be very nicely explained, probably you know this, that he was using graphic statics, and if you are looking at this sketch of the left part of the bridge, we see on the one hand the arch, we see on the other hand the columns and the deck, the bridge deck, and we recognize that the shape, the form of the arch is very special. It's very thin on the level of the support. You see it here, on here. It's very thin on the level of the support, and it's much thicker in the middle of the span, or let's say in the quarter point of the span. And the reason is that he looked at the compression line in this arch, and if you have loads on the one side of the bridge, this line will go up, and if you have loads on the other side of the bridge, this line will go down. And the intention was to have this line at the interior of the material. As long as you have the line at the interior of the material, there is bending. For sure there is bending, but this bending can be taken only by compression, and so you don't use a lot of reinforcement. That means he started with a very strong idea how the form should be developed in order to have a very efficient load-bearing behavior. And I think we see this on the right-hand side, structural design. This is what we are understanding under structural design. Starting with the forces in space, and then out of this going on, looking perhaps for a model to calculate this if it's necessary, and then in the next step to bring it to a real structure. And what civil engineers are normally doing, they are waiting till the architect brings a system, a structure, and then they are trying to put a system, an engineering system in. They are making this structural analysis, and then the answer is it works, or very often it is not working. And then there is an iterative process, and at the end nobody knows where this iterative process will end and what about the efficiency of the project. And perhaps it's interesting, this question, does something work, was never asked between Christian Kerez and me. Never. The question was always, if we are doing this, what will be the consequences? And everything works, but the consequences can be, they can be heavy, and they can even be a non-go. But if we are speaking about the consequences, then we are able also to go on developing the structure. And our model for articulating forces in space is fully based on graphic statics, a very old method that was already developed 300 years ago. As you see here, then Kuhlmann in Switzerland, at ETH Zurich professor, was strongly pushing this method. And we tried, together with Aurelio Mutoni in Lausanne, to push this method in a way that we are able to model all possible systems by the internal forces. And then what we are not doing is what is often done, as you see it here. You have the given structure coming from the architect, and you are trying to put a theoretical model in, and then at the end you are calculating the internal forces. We are trying to go the other way around. It seems not to be a big difference if you are looking at these two slides, but it is. Because, as I already mentioned, we are trying to start, as you see it on the top of this slide, with the internal forces, then trying to speak perhaps about how to articulate these internal forces, and then coming to the structure. And in order to do this, we developed a very strong methodology, starting, you see it here, with the cable going to the arch, then combining both cable and arch, then making a superposition of these arch cable systems, and so we come to the truss, and then at the end we are blowing up the struts of the truss, and we are coming to the beam. And we are not starting, as civil engineers are often doing, with this beam, with slender lines, the statics with this classical statics, where already the most important dimension in this direction is missing, not speaking about the dimension in the third direction. Here you see once more this principle, and what we are doing, we are trying to explain, to teach this to architectural students in the first year course. That means cables, arch cable, truss, beam, and then at the same time going in the third direction. Cable net, dome shell, spatial truss, slab. That means at the end, they are able to go with graphic statics. I will quickly show how this works. And they are able to understand and even to articulate and even to calculate such systems. And all of them have the same level of complexity. For civil engineers, shells are something very, very complicated, and you need computers. I don't know what. But for looking in this way at things, a shell is as simple as a beam or as a cable, and all these different systems have the same level of complexity. That means it's then also very easy for the students to use this different system in a very playful way. And I will also show that at the end the aim is to leave these typologies and no longer speaking about cables or shells, but only speaking about forces in space, and bringing these forces in equilibrium, and bringing these forces in relation to materials, bringing them in relation to structure in the sense also of architecture. Simple principle leads to diverse structural behaviors. That's very important. Teaching, I already tried to mention what we are doing. We have then a second year course. We are going more in the direction of materials, and at the end, master studies, we have a lot of special lectures where they can play theoretically or experimentally or whatever with this methodology. In research, we were strongly doing research in direction of computational design, then research by design, and also history of engineering was a very important topic for us, because a lot of things in civil engineering history are forgotten and can be in a very nice way reflected also today, to be able to be much more efficient in developing such structures. very shortly, this is something you understand. A man standing on this cable, and looking at this with graphic statics is easy. You only have to make equilibrium, for instance, in this node, and then at the end you will have something like a force triangle. You can put these force triangles for the different nodes together. Then you are coming to the force plan. You see it here on the right-hand side, this force plan and Cremona plan. And what's very interesting, if you are changing geometry of the system, immediately also the force plan changes, and you so can immediately understand how you have to articulate your system in order to also be able to articulate the forces. That means you are not going by trial and error, but from the very beginning, you immediately see in the way of parametric thinking what happens if you are changing geometry. And this is also very important for sure for architectural space, because proportions and all these things are for sure governing elements in the concept phase. You see here, playful with the students, we tried to also physically trying to understand how forces work, and a very nice example here, the pavilion of Caesar in Lisbon shows also in a very strong way how the method works. You don't only have this red line, red means tension in this tensile membrane, but we see also how the forces are going down in the towers. This blue line is leaving the tower. Then you need stirrups to put it back. You see how then the force interplay is going on. You see how these forces are going in the ground with these piles, and you see also that you need this horizontal slab on the bottom to close the overall system in a very simple way, and you can immediately understand if you are changing geometry what will happen with the forces, and so it's much easier to articulate the whole system. We are not speaking about bending, we are speaking about this arch cable system, as you see here. Easily to understand. This can be an internal or an external system. Also here you see on the one hand the force plan, and on the other hand you see the system itself. Then you can do the same thing for cantilevering elements as it is used here. You can change geometry from the point of view of curvature of the compression element and the tensile element, and you can play also with the rise, and so you have all the parameters from the very beginning under control. You need to develop such a system that is really corresponding to a form that is efficient also in the sense of statics. Eiffel Tower is a nice example. This was already done by Maurice Köchl in the same way, also with graphic statics. He developed the form, or you see here beams, or also beams with cantilevers or continuous beams. And what we are developing there is very similar to the representation of bending moments, but bending moments are something very abstract and never showing something about geometry, and never showing something directly about the internal forces. It's bending. We don't like bending, shear, torsion and confusion. We like much more compression and tension, and are trying to reduce everything to these elements. You can also do this with stress fields in the sense of theory of plasticity, lower bound theorem of theory of plasticity. Left-hand side concrete beam, right-hand side a steel beam. You see you have similar trusses at the inside, you have similar stress fields, but they are related to the material. But the principle is the same, independently if you're going with timber, with concrete, with reinforced concrete, with pre-stressed concrete, with steel, with synthetic materials. The principle is always the same. We already developed a book in 1996 together with Aurelio Muttoni and Bruno Türlimann, who was my PhD supervisor on stress fields in reinforced concrete. This were first step in this direction, and now we were able in the last 20 years to develop this further to really closed system. Here you see a frame, here you see another frame in steel. The first one was in reinforced concrete. You see also that the details, this frame corner for instance, can be handled with exactly the same methods. You don't have different methods for the beam and for the construction. You have the same method, and total thing is scaleless. That means it's not important if the building is big or small, and this is also the reason why it works as well for detailing as for big load-bearing elements. Here you see a little bit of resume. You see once more cables, arches, then this arch cable system and the trusses. Would be nice to elaborate for hours about this, but I don't have the time. But you can for sure intuitively imagine a little bit the philosophy behind, and also the third direction where you see these nice high-pass systems, the combination of high-pass systems, more complicated arch cable systems, or spatial trusses or slabs or whatever. You can always reduce it back to these very simple systems. I, by hand sketches, find out the order of magnitude of the inner forces. And the whole thing, as I already mentioned shortly, is based on the lower bound theorem of theory of plasticity. We are not doing something that it's approximative, I don't know how you want to call it. It's really, these are systems based on a very strong theoretical background, because we always have equilibrium, and that's the very most important aspect, and that's not always the case for a lot of works that are produced in a lot of civil engineering projects. Continuous force of flow in space, that's very important. Also the third direction, and I wanted quickly to show this in order to make perhaps a little bit easier understandable when I will now speak about these selected projects, and also a little bit about the development of the projects. But I think this is much more interesting than showing the final project. Some of the projects we will know, but what you will probably not know are a lot of anecdotes during the developing process, and I think these are not anecdotes, but this is how projects are developed. And for all of these projects, what's nice at the end, it's no longer possible to differentiate what was brought in by the architect and what was brought in from the civil engineer. I think this is very nice, that at the end you can no longer split this, and we don't even remember how this process was really running. We only remember a lot of anecdotes, but there is no continuity in the development for sure. You know this very well, projects you have developed by yourself. House in Forsterstraße, once Christian Kerez found me. That was more than 20 years ago, and asked me I would be interested to do a building together with him. They would have a very strong idea, because your concept, you will hear this lecture of your concept in some weeks. developed a house in Chur, something a little bit like a cantilevering system with walls standing one on the other hand in plane, and he had the vision to do this in space. And he asked another engineer, and this engineer told him that this is very complicated and he needs to buy a new computer program, and he has enough money to buy this program, and it was costing, in any case, 3 or 4 months to develop the system, and so on and so on. And then, as I mentioned, Christian Kerez phoned me, and then I told him, yes, we could try to develop a nice strategy and to develop rules how the system could work, rules that are interesting for the statics, but that are also interesting for the development of the architectural space, of the structure and of the concept of the architectural space. And then for me it was sure that in order to produce something like this, the idea behind must be very, very simple. If the idea is not very simple from the point of view of civil engineering structural design, then we will immediately lose control. And then what we did at the end, we developed a role that a wall has to be supported at least at one point. This seems perhaps a little bit strange. If you are telling to somebody you have a wall, yeah, you put it on one point, and the point must be in the middle. But no, this was for me not the point. It can also be supported by this point. Why? For sure, because this wall is not alone. This wall has colleagues in the building. It has a slab on the top, it has a slab on the bottom. And now, in order to rotate around this point, it has to be detached from the 2 slabs. That means the forces, tensile force here and the compression force here, are enabling this wall to stand even if it's only supported by one point, because it's at the interior of this integral system. But that means that on the other side somewhere there must be a counterbalancing wall, and you see very nice these 2 walls. On the one hand you have this one, who is who is for sure is only supported on this point, and then on the right hand side you have another wall, and this wall is only supported on one point. And so it's possible, by looking at this integrally in 3 dimensions, that you will be able, if everything is in equilibrium, to bring at the end these forces down through the middle core of the building. And as I mentioned to you, it's important to put it on one point. This can, for instance, be a wall. Then it's placed on the wall, but also the contrary can be the case. Also, this wall can bring a load down, and another wall is not standing on this wall, but is hanging on this wall. And also this is the case in the one or the other situation of the building. For instance, here, this is the case. This vertical wall is hanging on the wall on the top. And so it was possible, in combination with the slabs, to bring the system to work. What was the benefit? We had a very small flat, and it was very, 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 very small, very small dimensions to build the building, and it was very important to build spaces that seemed to be bigger than they are in reality. And for this it was very important to build spaces where you don't see the columns. Coming back to this example, if you are looking, for instance, here, this slab at this point is hanging on the wall on the top. And if you are in this room, you cannot understand how this span or this cantilevering is possible if you are not knowing that the slab is hanging on a wall 1 story higher than you are standing. On the other hand, also the total opening to the outside and bringing a landscape in for sure is also increasing this effect of giving the feeling that spaces are bigger than they are in reality. And as we are bringing the forces down in the center of the building, it was also very nice to have these closed spaces at the interior and these very open spaces at the exterior, but you always feel that there is light on the other side. It's never closed. You always have this transparency more or less filtered. Here you see such a situation also with a very big cantilevering slab, and also this slab is hanging on a wall that is a story higher, and you see very nicely how the landscape, the colors and all this atmosphere are coming at the inside of the spaces. Here you see classical plan, for sure you know the project. Here you see a little bit the principle I tried to explain to you now with blue and red, how these walls are standing one on the other one. And going on to the next slide, you see that also in the floor plan you can change the position because you always have the slab, and it's possible to bring these walls together. For instance, here they don't have to be in one line, they can also be detached. Here the whole system with not a lot of number of lines, but if you are now turning it around and looking at the inside, you will much better understand how this system works. For the slabs, we used pre-stressing, very sophisticated, in order to have this very nice concrete surface on the bottom of the slabs. We also like a little bit more complicated handling on site, and this worked very well in the sense of construction. The parking beyond this, under this slab you see in the slide, is without any columns, because we have these 4 walls that are used a little bit like a windmill, and by putting pre-stressing cables in, the deviatoric forces are replacing these columns, and so it was possible to build this 25 to 15 meters slab, this whole building without any column in the parking garage. Here you see how this was built with these pre-stressing cables integrated in these walls, and the curvature of the pre-stressing cables, easy to understand. They are able in these 4 points to take the loads of the whole building, because all these loads, as I explained, are coming down at the end through this middle part of the building. Here you see a last photograph of this very nice structure, also very radical construction, a concrete structure finalized on site, windows put in, and that's it, nothing more. Then the Leutschenbach School, you know it very well. Also here some ideas only. This was the first phase, because the competition was in 2 phases. In the first phase there were 2 teams that could work on. In the first phase we had a system without balconies. Then in the second phase we put this balconies in. They are for fire escape very important, so that it was possible to have very big interior spaces and to open everything at the inside by making the escape about these balconies. And also then in the second phase of the competition we had all these truss elements at the interior of the structure. You can imagine if you're putting these truss elements at the exterior, we'd have a lot of problems with building physics, because we you always have big forces, and then the slabs coming to this facade, coming to these trusses, and we didn't have the courage in the competition phase to tell to these people that we will, when we win the competition, we will put these trusses at the outside, and this was then only done in a later phase of the project when confidence was already built up between the planning team and the people from the canton and from the school. Here you see another picture of the competition phase, and you see at the very beginning we had on the ground floor and also on the fourth floor we had concrete walls at the inside. You see it here, something like rings, and then the truss elements on the top of it. The same in the fourth floor, you see it here. And only then in the last phase of the competition, we changed to a total system with steel trusses for the overall load-bearing structure. It's a mixed structure with concrete slabs, but all the wall elements as trusses. And here you see models of different options we tried to develop in the sense of statics, in the sense of architecture, and we were in a very playful way trying to find out what could be the optimum in the sense of structure and also in the sense of architecture. And then, yes, the process went on. Here you see something that is already very close to the final version, but you see on the ground floor we have truss walls, and then there was the question, are these truss walls really needed? And what could be the minimum? What are the consequences if we are trying to reduce these trusses as much as possible? And the answer was, from our side, the consequences are that it's even better. And so we went one step further and put the whole building on 6 tripods. And also here, the reason is rather easy. You have all the loads on these tripods. If you now have horizontal loads, for instance, earthquake loads, then you have the whole vertical forces going through these tripods. And if you are bringing these lateral forces, they will stay in the tripods. And on the one side they will be increased, on the other side they will be decreased. They will have an inclination, and as long as this inclination is at the inside of the tripods, you don't have any problems. That means the angle of the tripods was given out of these considerations, and also from the point of view of architectural design, that was a criterion that could very nicely be used. Here you see a model we built 1 to 10 for a big exposition once of this steel structure. On the top we have the gymnastic hall only lying on 4 points. Then we have these 2 transverse trusses, and these 2 transverse trusses are bringing the forces down through these middle trusses to the tripods, and the outer facets of the 3 stories of the school building are also hanging on these transverse girders here on the 4th floor of the building. The open floors on the ground floor and this 4th floor are more public, aula, library, mensa, and so on. And the middle tracts are more private, 3 levels of classrooms in the lower box, and as I already mentioned, the gymnastic hall on the top box. And also here, for sure, when we put these trusses at the outside, we had a lot of problems with building physics we have to solve, and we solved this by a most efficient and very simple detailing we developed by ourselves, but I think this would lead much too far to explain all these details here. You see a little bit the building process, foundation, then you see the situation when we build tripods on the right-hand side. Here you see how we assembled these main trusses, these two transverse trusses having enormous, to take enormous loads, and then at the end some plans of the whole system. You see also this detailing with this very big cantilevering element there, only understandable also here. Same principle as for the house in Forsterstrasse, if you understand that the slab is at the end hanging on this truss. For the planning, that was it was a lot of work to do in order to have all these openings at the right location from the very beginning, and so on and so on. You can imagine what this means, but there was a lot of detailed planning was necessary, but at the end the process on site was not so difficult. The slabs also here, formwork of the slabs, then you see how this was developed. You see then when scaffolding was taken away, this is always a very difficult moment for the civil engineer, but at the end we were very happy to be able to bring this building to a good end. This is the edge of a classroom. This is a last view from the side on the structure, and also here you see now these trusses are on the outside, and that was very important for us in order to have also this connection between these different blocks, because if you have them at the inside you don't feel them and you don't understand really the structure. On the other hand, from the inside you can see them very nicely. This was a strong process we were able to develop during the planning phase. And here also you see this very strong cantilevering of 13 meters on the bottom, and these bases are very strong, and it was also here possible to put glasses in without any frames. This needed a reduction of the height of the building, and this was also in fitting to the architectural idea of connecting outside and inside, but also to making this very high load of the building, this flying load, a little bit more dramatic. House with the missing column, it's a Haus Müller. It's a Haus Müller in Zurich, not a Haus Müller in Prague, but nevertheless, it's also an interesting structure, but not comparable to the school of Leutzenbach. You see, it's a building with 3 levels of flats, only 3 flats in the building itself. And the idea was to go with a windmill-like system, starting with 3 cores. One core is here, then another core is on this side here. You see it with the elevator, and the last core is on the bottom here with installation tubes. Staircase core, core with the elevator, and the core with the tubes. And then we have these cantilevering elements going out from this core, and they are connected. Only the last one is lost. For the last one there is no connection at all. And in order to bring this one under control, we build it a little bit like a curved element, like a banana, and then with cables we brought it in the horizontal position during the building process, and so it was possible to use these cables as columns in the further process, because the reduction of a tensile force in the cable is the same as the increasement of a compression force in a compression column. But this is perhaps a little bit tricky, but that was the way we solved it. And then you see also here, this is also a mixed structure. This was an interesting building phase with this structure in space without any element, any reference element. It was not so easy for the contractor to build, but he did it very well. And then in the second phase, the slabs were put in. Here we had a lot of problems with these connections, where we had also requirements on fire resistance, and all these details we tried to develop them by ourselves, and then at the end to test them also in a laboratory. But also this leads much too far to explain it here in detail. But you here see very nicely the concept with these three cores, and then the beams, you don't feel them from the exterior, but they are very present at the interior of the building. You see it here. They are very present at the interior of the building because they are coming down, and you even have to, yes, you are able to walk under the beams, but nevertheless they have this very nice separating function of the space. Also on the left-hand side you see this tensile element we used to bring the beam in horizontal position, and for additional loads is working as a column. You also here see very nicely how the colors of the outside are coming at the inside of the building. Also here this relation between exterior and exterior that's very strongly developed in the project. Now some projects that are a little bit more recent. Incidental space for the Biennale in Venice. That was more a question of how to develop in some way spaces that are a little bit strange, a little bit new, a little bit playing with the perception of spaces. And the next project I will show goes in a similar direction, but it's something totally different. But the idea is more or less the same. And the idea was for this Swiss pavilion at the Biennale, how is it possible to produce a space that it's very interesting from the point of view of perception, but where you are a little bit irritated and difficult to really understand what's going on. And we started with the idea to make the limiting elements of the space variable, to have, for instance, a floor that you can change in position, also the inclination, also the walls and the slab. And then there are ideas to do it perhaps with textiles. There was the idea to do it with plates and walls, but we then immediately saw that this is very difficult, not only from the point of view of kinematics, but also from the point of view of techniques. And then at the end, we had the feeling that it could be possible to go the other way around, to produce a form where it's not possible to really understand what are the inclinations and what are really the limitations of this space, going the other way around to do something fixed, but more or less giving the same illusion if you are entering the space. And then the idea was, how can you develop, how can you, find something like an incidental space, a space without any criteria, a space developed by chance. And Christian Kerez then had a whole semester with students in order to produce such a space. And then at the end, there were 20 different options, totally different principles and concepts. And then at the end, they decided for a space that was produced some way in using something like waste paper and putting all this waste in plaster, and then at the end cutting the plaster, taking all these elements out, and then at the end you have something like a cave with a special form. And then they did several experiments, and then at the end they fixed one of these real experiments they did, and they used then really this form and scaled it up. And you know, also the process of scaling up is already very interesting. A lot of interesting aspects are happening also in the sense of perception and so on and so on. And but we also had to do it then, and we had at the end to produce it. And perhaps you know this, this I don't know how to call it, this structure. It's not a building, I don't know what it is. It's perhaps something like an organ, something like a stomach, I don't know. But nevertheless, it's 5 meters high, 7 meters long, have a surface of more or less 200 square meters. And then the question was how to build it. What's the thickness? What could be the thickness of such a structure? My answer was something around 3 centimeters. Okay, then let's choose 4 centimeters on the bottom part, 2 centimeters in the top as the thickness of this shell-like structure, and let's try to build it. And then we found a shotcrete specialist who was able to help us to build it. The formwork was done on the one hand by something like foam glass, by milling it, everything for sure digitally developed. And on the other hand, we also used a second principle, and the second principle, as you see it on the right-hand side, was done by 3D printing, because milling you can only if the milling head is able to enter. If you have complex geometry, it's no longer possible, and all these elements, but this was not possible. We produced them by 3D printing, the formwork, and the other ones by milling. And then at the end there was a shotcrete layer between 2 and 4 centimeters was then put on it, and at the end on site all these different elements were transported to Venice, more or less 200 elements, and then they were assembled then on site in the Swiss pavilion, as you see here, and they were glued by an epoxy glue. Here you see a lot of people, students, building this 5-meter high building, and we at the end had to put this entrance in so that it was possible to enter. And here you see some cosmetics at the end. This was during the inauguration of the exposition. Christian Kerez together with the Swiss minister, and they were sitting inside and were trying to understand what was going on in their perception by being at the inside of this structure. Here a last picture from the outside, and the entrance is somewhere here. That means you can imagine a little bit the proportions as we have seen before, 5 meters high and 7 meters of length. So far for this project. Now I'm coming to the pavilion for the Kingdom of Bahrain for Expo 2020 in Dubai. And as I already mentioned, the idea behind is more or less the same, but the product is something for sure totally different. But it's also about perception of space. And you see here first pictures of these buildings. This is a floor plan, 25 to 25 meters. We are more or less in the proportions of the, in the dimension of the school building of Leutschenbach, School of Leutschenbach. And here you see a little bit the rooms that are placed around, everything underground, and what is visible is only at the outside this cube. And not to forget on the left-hand side, a small building for the King of Bahrain. He had special possibilities to enter the exposition, but the main building is this cube coming out of the ground, and nevertheless 3 or 4 meters also underground. And this was what Christian Kerez showed me the first time. He tried to develop it with other engineers because he had the feeling that it's very simple, only one load-bearing element, a column. Multiple of these columns should be easy to manage, but they had problems. They were working on the project for more or less half a year, and the engineers always told him there is a column missing, and then they put an additional column in. And then by putting an additional column in, they found out there is another column missing. And this game went on, and at the end, it was not possible to come to a good conclusion. And then, yes, he came to me and asked me if I see a solution and if I could help them to do it. I told him, yes, we can try to find a solution, but we must find very quickly a solution. And if we are not able to find it, then yes, then the game is lost. And then I made the first concept. I told to him it doesn't make any sense from the point of view of civil engineering to look at all these columns, because you will always have peaks. It will be difficult to define what about buckling, and this is probably the problem the other engineers have. Let's start the other way around. Something like an explosion could be a nice idea, saying we have one point, and from this point there is an explosion in all the different directions, and then we only use 3 of these different lines, and these 3 lines we put them in the system, and then not only as a tripod, but we are going on with the lines also in the other direction to the facet. And then we are trying to connect 3 or 4 or 5 of these tripods, and then we are looking what happens. We are telling to the system, you will not buckle, but at the end we will try how to solve the buckling problem, but we will eliminate the buckling problem ideally, and then we are looking what's the minimal dimension for these columns, because also that was a very big topic for the engineers. Would be nice to have columns like this, 25 meters of length, but in the idea of perception of this space, it would perhaps be nice to have columns of only 15 centimeters or 25 meters long. And then we found out, no, not 50, not 15, 10 or 12 is enough if they will not buckle. But in order to take the structure of the facet, this will be enough. And then what we did, you see it in this slide, we produced families of columns. This is now a section through these columns, and now you will see these columns growing. The red ones are the tripods connected by these horizontal lines. And these tripods, they are taking all the loads. And the other ones, they are used to stabilize the red ones. And the green ones, the third hierarchy, the last category, is used to have the last elements you need to hold the facet. And so we had this rule, and I think this is very important, and perhaps you could feel in all the stories I told to you for the other projects, this question of having rules is very, very important. And I fixed the rule to put in these tripods and to have these connections. And Christian Kerez liked very much these rules. Another rules was that we should evitate horizontal and vertical elements, because then you already have the feeling it's a column, it's a beam. It should not be beams, it should all be by a Mikado-like column system. And so we evitated angles between 0 and 15 degrees and angles between 80 and 90 degrees and so on. And then at the end, we had not a lot of options. They produced 100 of models for sure, because they are very quickly produced. And at the beginning, they tried to bring it from an architectural point to the optimum, to a very strong differentiation of density and so on in this forest. And they tried it out, and they were never very satisfied by. It's a sculpture, and yes, they were never satisfied by the final solution they had. And what was then very nice for me, that at the end Christian Kerez told me what we developed now with these very simple rules is much stronger than everything we developed before, only by artificial, let's say by intuition. And what's also interesting here, then the idea, instead of making all the columns with a diameter of 12 centimeters, these columns of the tripod, we will do them a little bit thicker. We will do them 14 centimeters. And this was not very easy to recognize, and only a few people recognize there is this differentiation, but also this subtle variation we already did also with the struts in the school of Leuchtenbach was also a very interesting aspect. We polished the steel and put a transparent color on it. Here you see a note. Here you see the finalized structure. And another question was, what about the windows? And for the windows, a little bit relating to this, to this Arabian window-like systems. The idea was to develop windows like slats, and having the columns perforating these slats, and then at the end you don't see where the columns are ending. They are penetrating the facet through these voids, and on the other hand you have the light coming in, very nicely filtered with this this yellow sand that was lying at the end a little bit on the structure, bringing a very nice light at the interior of the structure. Also the facet was a development we did with a lot of engagement. You see how this was at the end developed. You see here the idea I already mentioned. Here prototypes we did in order to look at the feasibility. Then the outer surface, it was very important for Christian to have a little bit of structure in this surface. Not possible to build it totally plain, but to have a little bit of structure in it. And this was then differentiated between the code itself and the regions where the windows are. If you look a little bit more in detail, there is much more precision, and so there is this variation on the overall surface. Here, see a little bit the effect of the space. There was this exposition on the floor, and also playing with this density. We were totally, at the end, it was very interesting to see that the perception of this space, even working for months and years on it as a planning team, was once more totally different. It was much more open. It was something, yes, it was something different than everybody had imagined during the process. Now, the last, this is only for some few minutes, and it's a movie about this China pedestrian bridge. We won a competition now nearly 2 years ago as an invited team in Nanjing. We won this competition. Now we are in the planning phase. Nobody knows if this bridge will be built and who will build it, if it will be built, but nevertheless, we are still involved now in the planning phase. And also here we tried to make something, yes, that is a little bit out of what is normally done by thinking on a pedestrian bridge. Nanjing, you see it here. It's a bridge over this river. On both sides there is a park, and in these parks there are these passes you see, very serpentine-like. And now we tried to go on with these passes in the park and to bringing these passes in space. That means something like passes in a park, but not grass at the exterior, but air. Nothing than air at the exterior, and then at the end it was the question how to develop such a form. Then we decided to produce more bridges in parallel, and 2, 3, 4, 5, and at the end we decided for 3. You see a little bit the context. Perhaps you know Nanjing, this town that is in a very strong development, also with a nice university where they are strongly interested in architecture and space, a lot of technology. This bridge by Zaha Hadid, not far away. Then the question of the park, and the region there is named with the name of an old technique they have for painting, and we use this a little bit as a reference for the bridge design, and their different aspects are important. On the one hand, the verticality that was very important also in our project. Then for sure, the horizontality is always a topic in a bridge, but also how to go vertical direction, and this density. This density we also try to experience in the incidental space and also in the Bahrain project. And then what we did at the end, we did 3 lines of the bridge, and these lines are conducted in space and are connected by staircase elements. That means all the elements, all the load-bearing elements are accessible. There are no pylons, there are no cables, elements that are only there to support the desk, but everything you see in this bridge is accessible, and you can go over all of these different elements. And the idea behind is to have something like a 3-dimensional arch cable system, as I tried to explain at the very beginning, something between a virandel and between a truss. And the idea was to produce a form finding with only compression and tension in the elements under dead loads, and bending only appearing if you have additional loads. That was the rule. And this rule was also very fruitful in the sense of how to articulate density, in the sense how to articulate the whole system, how to go with these curvatures, because that was very important for us, that when we are walking over this bridge, the view is changing continuously. You see it very nicely here. You can go on these different levels. You can even change the level if you want to do it by passing the bridge from one level to the other one. And normally, if you are passing such a bridge, the view is more or less the same. You are changing position, but from the point of view of three-dimensionality, the view is more or less the same. And here we tried really to play with this integration of the whole system. The span is not yet totally fixed. It's something around 140 meters, but it's always a little bit changing depending on the boundary conditions they are bringing us from these different regulations, and these things are not yet totally defined, but we are now going on in the process, and it would be really nice if you would have the opportunity to build this bridge. But nothing is clear in our world. We live now in 2023, but we will see. I have a last slide. I want always to finalize with a small quote. 1959, then I was 2 years old when Pierluigi Nervi quoted that it's about finding ways to render the collaboration between architects and engineers more and more fruitful. Collaboration which has to start at the beginning of architectural planning in order to avoid formalistic access as well as technically impracticable solutions. That's my message, and it's still okay. Even 60 years later, I think it's more valuable than even then. And we should reflect on this and really going on trying to bring these disciplines together to reconciliate really these disciplines and also the new disciplines that are now involved when we are developing projects nowadays. Thank you very much.
So I have the first question. Could you probably describe how you work together personally with Christian Kerez? If you have meetings and you discuss together, or Christian will just say some few ideas and then you work separately, or how does it work?
Well, I would say this collaboration is perhaps extremely organized, but also extremely chaotic, because when we are developing projects, and that's the most interesting moment during the most work competitions for sure. If we are developing these projects during the competition, then the final decision often is only taken 1 week before before the competition should be finalized. But then we have already discussed a lot of different options. And so then at the end, under time pressure, it becomes perhaps more in an intuitive way done very quickly to an end where we really feel that this could be a good direction. And what's interesting, the main decisions that were then taken at that moment, they will be alive to more than 90% till the end of the project, because they are always based on rules. But the process itself, also already in this phase, I would say it's it's very special. We don't need a lot of words. We don't need a lot of sketches. So it's always developing in a very strong way of communication, a lot by telephone even. And what's also for me very fascinating, Christian is able to explain to me an idea and I see it immediately plastically and I can immediately interact on telephone and tell to him, yes, but would it not be interesting perhaps in the sense of architecture, perhaps to develop the structure then in this and this direction. And so this kind of process is then also very, very straightforward from the moment the decision is taken, because for sure at the beginning, you know this very well, everything is open and everything is possible, and then we are trying to find out from the context what could be a good concept, and then, yes, it develops in perhaps even in a magic way.
So you have somehow feeling that's the idea we want to present. Like at the end you develop it, that you have both feeling that that's it.
Yes, but already in this phase it's not so clear who is deciding. For sure, the overall idea, what are the boundary conditions, what could be the topic of the architectural concept and so on, a lot that's coming from Christian, but it's very, very open, as I tried to explain for the incidental space. And then it was important for me to understand what's the goal. And then often I have a crazy idea and I speak out this idea, and 1 minute later I have the feeling this was stupid to tell this, but it was an idea that is really helping to push it. And then he asks something, I tell him possible, but the consequences are horrible. And then he stops and tries. And so it's something that it's very flexible at the very beginning, but nevertheless, in would say in a magic way, focusing to then often a rather strong concept. But that has a lot to do with this way of really playing with the parameters and looking at the consequences, as well for him as also for me. I think this seems for me to be very important, and this is never the case in a similar way with other architects.
And would something like you showed be possible without computers?
Yes, for sure. At the end, the computers are helping. But as I told you, or tried to tell you, the basic concept of these curves was for the bridge not to have bending under dead loads. That you can do it by graphic statics. You can do it by hand. As Maya did it, it's the same. He did it but you can also do it in space. And for sure, you can calculate 20 times 48 by a small computer or in your head, but you have to understand that you have to calculate 20 times. That's important. But at the end, the tools, also in the civil engineering world, I feel they are very dangerous. Because you see a lot of trees and you're also able to manage a lot of trees, but you don't see any forest anymore. And that's a big problem. And the other way around, as I mentioned also at the very beginning, the big problem is that you are lost with these computer programs if you are starting with a given structure and you are trying to find out the internal forces and to optimize it. I think there is no optimization in such a project. There is only a development in a strong direction, but it has nothing to do with optimization. Efficiency, yes, and engineers often are looking for this optimization, and that's not a good way to look at things, because you have to start with a strong system, as I showed with these tripods, and then at the end, what should I optimize in these tripods? I can position them. I'm totally free to position them because the concept is so efficient and so strong. And then at the end, the calculation, if it works without buckling could be difficult and could perhaps be needed to use a computer, but that's obvious for everybody. If the length is too big, you have to put something in between, and then you can look with your eyes and play with this, and also understand that if one of these columns is buckling, nothing happens. That means if the architect asks you if it's possible to have some longer columns, you can immediately say yes, because if they buckle, they will buckle, no problem at all, because system will not collapse. This can even be nice, but if you're looking from the point of view of analyzing a structure, then you have an impossible solution and it's not working. But that's not the case at all if you're looking integrally at this system.
And how is it with responsibility? Do you have sometimes fear?
I think responsibility is something, yes, very human. Also, let's say fear is something very human, but also something very, very subjective. Because the more, let's say, sophisticated this system seems to be, the more I'm always trying to have a simple idea behind, so that I'm always able to make plausibility proofs without computer and even without more or less, because it's not so difficult to find out the force and to divide it by a section, and then you have already the stress. I think it's not so difficult if you are really understanding how things are developed, and the more sophisticated, or the more, let's say, you are producing something that is not so often done, then the more you are looking on the details, the more you are waking up during the night and you are making such considerations, and at the end it's this that is helping us to avoid accidents. But the more, let's say, complicated the systems are, the less the risk that something happens. The big problems appear in simple structures where mistakes are happening and nobody realizes that these mistakes are happening. But on the other hand, it's a question, this responsibility, but that's also very personal. As an engineer, for me it's very important to understand everything I'm doing in a project from the scratch. Everything, that there are no gaps in the, and this is always done like this, and so you can quickly use a computer program and then it works, but everything is really something that I understand in a simple way from the very beginning till the end, and that helps also a lot for these questions of responsibility, for sure.
Thanks. Do we have any questions in audience? Můžu přinést? Ano, máme tady, jo, úplně nahoře pán. Maybe I will quickly ask, the Switzerland is known that you build from concrete mostly, but you show also flat house from steel. So it's something what is not used to in Switzerland. So are you happy to use steel also in Switzerland?
Yeah, but in Switzerland, in the French part of Switzerland, they are using, for instance, much more steel. In Lausanne, there was this big company, and now, but with Christian, we build a lot in steel and a lot in concrete, but also in steel. But with our office, we're also very strongly involved in timber construction, masonry. I'm originally an expert in masonry. We also developed a lot in masonry, also pre-stressed masonry, a little bit more advanced masonry systems. But material, also this is something in the engineering world that from the point of view of statical design, that very different schools, very different people, very different professors, very different researchers were going with timber, going with steel, going with concrete, and everybody had the feeling that it's totally different from material to one material, and all the other ones are not understanding a lot, but they are understanding really the quintessence of load-bearing behavior in. And there were these different ways a little bit of looking at things, and we always tried to show to the students that not everything is the same, but things are much closer together than it was developed out in history. Are much closer together, and the main principles are the same. For reinforced concrete, you have cracking, and you need reinforcement in order to take the tensile forces. If you're looking at a steel girder, you have a very high tensile resistance, but these thin plates, if you are compressing, then they are buckling. They are putting these ribs in. It's exactly the same, but the other way around. One is tension is the problem, the other material compression is the problem, but the problem is exactly the same. You only have to change the plus-minus sign, and you can solve it with exactly the same principles. And they did it, but they didn't realize that the ones are using steel stirrups at the interior of concrete, the other one ribs in the steel. They are doing the same thing, but they are not understanding that they are doing the same thing, because these are two different disciplines, and it was developed with a totally different concept in mind. And I find these considerations very interesting.
Good evening. Professor Schwartz, thank you very much for your marvelous lecture. You're a great inspiration not only for ETH students, but also for our students and for us as teacher as well. My question is, you use quite often pre-stressed cables in your architectural projects. Do you have any negative experience with loss of pre-stress force in these cables, in the pre-stressed elements? Thank you.
Yes, this is a very interesting question. Thank you very much. Also here, I could elaborate for 2 hours now, but let's try to make it very, 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 very compact. If you are looking, I start a little bit in a strange way to answer your question. If you are looking at this, let's call it Zurich school with theory of plasticity, then you can say that there is no big difference between reinforced and pre-stressed concrete. You have concrete and you have steel. But with pre-stress, if you are pre-stressing your element, you are able to bring internal forces from the very beginning in your system. And what we are trying always to do, and what was always done, is to bring in these forces in a positive way, in a way that they are helping. But on the other hand, if you're looking from the point of theory of plasticity, this force you are bringing in, this ominous pre-stressing force, is not at all influencing the failure load of your element. And that's perhaps a little bit strange for you to hear, because it's only an Eigenspannungszustand, is only an initial state of stress, and you can use a pre-stressed beam, not pre-stress it at all, load it to failure, it will have exactly the same failure load as the pre-stressed beam. Therefore, if I have a loss for any accident of the pre-stressing force, no problem for the load-bearing behavior in the sense of ultimate limit state, in the sense of failure of my system. No worries at all. But, as I mentioned, by pre-stressing, I can help the beam. Because if I have a beam like this and a cable like this in the beam, then I can calculate in my head the load of the beam, and I can calculate in my head, it's only a force triangle, the force I need in my cable to exactly compensate this dead load. And at that moment, when I'm pre-stressing the cable, the beam exactly to that load, what results? A given tensile force in the cable and a horizontal compression force in the beam. That means no deflection, no deformation at all. And that's the advantage. And therefore, we pre-stressed all these slabs in the house of Forsterstrasse in order not to have problems with the window glasses, because if you have creeping in these slabs, then at the end we will have problems with the glass that will be broken. And in this sense, if we are bringing this force in, that can easily be calculated, and if we are putting ejection mortar in, you will not have additional losses than the ones you are putting in the calculations, some percent. Then you have really the possibility to tell to the structure by putting in these forces how the structure should work. We did the same with this curved beam, putting it down by an exterior cable. And that's also one of my messages. I didn't have any time to tell about it today, that we can tell to the structure how the structure should work. And in this sense, it's important to bring ductility in and to bring in systems that are as less sensitive as possible. And this question of loss of pre-stressing in a cable, there is no sensitivity at all. From the moment you have the cable, you have already enough resistance, and you have a more or less adequate pre-stressing force in it. You only have something between 10 or 20% of the deformations you would have without this pre-stressing. And now if this is 10 or 20 or 25% is not so important. You don't have this 100%. You only have a small rest of the deformations you would have without the pre-stressing. Sorry for being so long, but it's a very essential question, I think.
Any other question in the audience? If not, thanks a lot for your lecture. Also, public can come privately for private questions if they are interested in. And we will welcome your colleague from ETH Zurich in November, Tom Emerson in November, and then Jürg Gonzett also from Switzerland. So we are looking forward, and thanks a lot you came to Prague.
Okay.